Listening practice, engineering drawing laboratory principles, practices, and applications preface the role of engineering drawing in modern design in the dynamic landscape of modern engineering, where digital tools like CAD and 3D modeling dominate. Engineering drawings remain the cornerstone of design communication. These drawings transcend technological trends, serving as a universal language that bridges disciplines mechanical, civil, electrical, and architectural. They ensure precision and clarity, enabling global teams to collaborate on projects with shared understanding, adhering to standards like ASME Y14.5 and ISO GPS. Beyond technical documentation, engineering drawings are legal contracts that safeguard quality, compliance, and safety. While CAD enhances efficiency, the core principles of scale, projection, and annotation endure, underscoring the timeless value of mastering engineering drawing. Scope and objectives of the book. This book is crafted to blend foundational principles with modern applications, guiding readers from basic concepts to advanced techniques. Structured progressively, it begins with line types, geometric constructions, and orthographic projections, advancing to sectional views, dimensioning, tolerancing, and CAD integration. Key objectives include developing proficiency in interpreting and creating multi-view, isometric, and schematic drawings. Mastering standards for precise dimensioning and geometric tolerancing. Leveraging CAD software for 2D drafting and 3D modeling. Understanding how design choices impact manufacturability and safety. Designed for students and professionals, the book combines exercises, real-world examples, and CAD tutorials to bridge theory with practice, fostering skills critical for collaborative, innovative design. Lab safety protocols and best practices. Safety is paramount in environments where designs transition from paper to prototype. This section emphasizes personal safety, use of PPE, ergonomic practices for drafting, and machine operation protocols. Workspace integrity, cleanliness, equipment maintenance, and secure data management to prevent errors. Accuracy as safety, rigorous checks to eliminate design ambiguities that could lead to hazardous outcomes. Emergency preparedness, awareness of exits, first aid, and incident reporting. By embedding safety into every step from precise drafting to lab execution, readers cultivate a mindset where innovation coexists with responsibility. Closing remarks. This book aspires to be more than a technical manual, it is a gateway to becoming a conscientious engineer. By marrying traditional drafting rigor with digital tools and safety awareness, we prepare readers to contribute meaningfully to a world where precision and safety are inseparable. Let this journey through engineering drawing inspire not only skill but a commitment to excellence and ethical practice. This preface sets the stage for a comprehensive exploration of engineering drawing, emphasizing its enduring relevance, structured learning, and the critical role of safety in shaping adept, responsible professionals. Chapter 1, Introduction to Engineering Drawing. 1.1 Fundamentals of Technical Drawing. Technical drawing is the disciplined art of representing physical objects, systems, or processes through precise visual guidelines. Unlike artistic sketches, which prioritize aesthetics, technical drawings prioritize accuracy, clarity, and universal interpretability. Key elements include orthographic projections, multi-view drawings, front, top, side, that depict an object's true dimensions. Pictorial representations, isometric or perspective sketches for 3D visualization. Line conventions, solid lines for visible edges, dashed for hidden features, and phantom lines for alternate positions. Annotation, labels, notes, and symbols to convey materials, processes, or assembly instructions. These drawings act as blueprints, bridging imagination and reality across mechanical, civil, and electrical fields. Mastery begins with understanding geometric constructions, e.g., bisecting angles, drawing tangents, and evolves into interpreting complex assemblies. 1.2 Importance of precision and standards, ISO, ANSI, etc. Precision in engineering drawing is non-negotiable. A misaligned dimension or ambiguous symbol can lead to catastrophic failures, costly rework, or safety hazards. Global standards ensure consistency. ISO, International Organization for Standardization, governs symbols, tolerances, and projection methods, e.g., ISO 128 for drawing conventions. ANSI, American National Standards Institute, specifies practices like dimensioning rules. ANSI Y 14.5, for U.S.-based projects. Geometric dimensioning and tolerancing, GD&T, a universal system, ASME Y 14.5/ISO 1101, to define permissible variations in form, orientation, and location. Standards harmonize collaboration across borders, ensuring a 10 mm hole in Germany matches one in Japan. They also serve as legal safeguards, holding designers accountable for compliance and quality. 1.3 Tools and materials in the drawing laboratory. While CAD dominates modern workflows, traditional tools remain vital for foundational learning. Manual tools, drafting boards and T-squares, for aligning orthogonal views. Compasses and dividers *, to construct circles and transfer measurements. Templates, predefined shapes for symbols, e.g., bolts, electrical circuits. Materials, pencils, grades like 2H, light, 2HB, dark, for varied line weights. Vellum/grid paper, durable, semi-transparent medium for ink or pencil. Digital transition, printers/plotters, convert digital designs to physical blueprints. Storage solutions, secure cloud or local backups to prevent data loss. Lab best practices emphasize cleanliness, tool calibration, and ergonomic setups to reduce errors and physical strain. 1.4 Introduction to CAD, Computer-aided design. CAD revolutionized engineering by digitizing drafting processes. Key advantages include efficiency, rapid edits, copy-paste functions, and reusable templates. 3D modeling, virtual prototypes for stress analysis, interference checks, and photorealistic rendering. Collaboration, cloud-based platforms, e.g., AutoCAD, SolidWorks, enable real-time teamwork across continents. Integration, seamless links to CAM, manufacturing, and CAE, simulation, tools streamline workflows. Despite its power, CAD relies on foundational principles. A well-trained CAD user understands why a section view clarifies internal features or how tolerances affect CNC machining. This chapter's exercises will transition readers from paper sketches to basic CAD commands, blending tradition with innovation. Chapter Summary. This chapter establishes engineering drawing as the language of innovation, where precision meets creativity. By grounding readers in standards, tools, and CAD's potential, it prepares them to advance into complex techniques, always mindful that a single line can shape the future. Chapter 2, Geometric Construction and Basic Drafting. 2.1 Lines, Angles, and Curves, Manual Drafting Techniques. Technical drawing begins with mastering fundamental elements, line types, object lines, solid, thick lines, 0.5–0.7 mm, for visible edges. Hidden lines, dashed lines, short gaps, for obscured features. Center lines, alternating long and short dashes for symmetry/axes. Angles, use triangles, 45 degrees, 30 degree/60 degree, and protractors for precision. For example, a 30 degrees angle can be drawn by aligning a 30 degree/60 degree triangle with a T-square. Curves, employ French curves or flexible splines for irregular arcs. Use a compass for circles and circular arcs. Best practices, maintain consistent line weight, sharpen pencils, e.g., 2H for guidelines, HB for final lines, and clean tools to avoid smudging. 2.2 Constructing geometric shapes, polygons, circles, ellipses, polygons, hexagon. Use a compass to draw a circle, then step off 6 equal arcs along the circumference to mark vertices. Pentagon, apply the divide the circle method with geometric constructions. Circles, use a compass with steady pressure, pivot from the needle point, not the pencil. Ellipses, trammel method, slide a strip of paper along axis to trace the curve. Template, use ellipse guides for standardized sizes. Tips, verify symmetry with center lines and check congruency with dividers. 2.3 Dimensioning and Scaling Principles, Dimensioning Standards, ISO 129, requires dimensions in millimeters, placed above dimension lines. ANSI Y14.5, uses dual units, mm/inches, and aligns text horizontally. Scaling, full scale, 1:1 for small objects. Reduction scale, 1:2 for large objects. Enlargement scale, 2:1 for intricate details. Avoid errors, never duplicate dimensions, use reference dimensions, in parentheses, if needed. 2.4 Lab Exercise, Manual Drafting of Basic Geometries Objective, draft a composite figure, e.g., a hexagonal bold head with a scaled washer, using manual tools. Steps: 1. Setup, secure vellum to a drafting board with a T-square. 2. Construction, draw a hexagon, 20 mm side length, using a compass. Add a concentric circle, washer, scaled at 1:2. Include hidden lines for threads. 3. Dimensioning, apply ISO/ANSI standards to label sizes and angles. 4. Review, check line weights, erase stray marks, and verify scale accuracy. Evaluation criteria, accuracy, plus or minus 0.5 mm tolerance. Adherence to line conventions and dimensioning rules. Neatness and clarity. Chapter Summary. This chapter bridges theory and practice, emphasizing that manual drafting cultivates precision and spatial reasoning skills vital even in a CAD-dominated world. By mastering lines, shapes, and standards, learners build a foundation for advanced design, where every stroke reflects engineering rigor. Up next, Chapter 3 explores sectional views and advanced dimensioning, integrating these basics into complex technical communication. 3.1 Principles of Multi-View Projection. Orthographic projection is a systematic method for representing 3D objects in 2D through multiple views, ensuring accurate communication of shape and dimensions. Key principles include 6 principal views: front, top, right side, left side, bottom, and rear. Typically, 3 views, front, top, right side, suffice for most objects. Projection planes, imaginary planes, horizontal, vertical, profile, onto which the object is projected. Line conventions, visible lines, solid lines for edges directly seen. Hidden lines, dashed lines for obscured features. Center lines, alternating long/short dashes for symmetry or axes. Alignment, views must share common dimensions and align using projection lines to maintain consistency. 3.2 First angle versus third angle projection systems. First angle projection, ISO standard, common in Europe and Asia, the object is positioned behind the projection planes. View arrangement, right view appears to the left of the front view. Symbol, a truncated cone with the front view on the left. Third angle projection, ANSI standard, predominant in the US, the object is placed in front of the projection planes. View arrangement, right view appears to the right of the front view. Symbol, a truncated cone with the front view on the right. Key difference: first angle, observer looks through the object. Third angle, observer looks at the object. 3.3 Creating orthographic views, front, top, side, step-by-step process. 1. Select the front view, choose the most descriptive face, e.g., shows key features or natural orientation. 2. Project top and side views, use construction lines aligned with T-squares and triangles. 3. Transfer dimensions, use a miter line to maintain alignment between top and side views. 4. Add details, include hidden lines for internal features, e.g., holes, slots, and center lines for symmetry. 5. Dimensioning, apply standards, ISO/ANSI, to place sizes in the most appropriate view, avoiding clutter. Best practices, avoid redundant views, use section views if needed, covered in later chapters. Ensure hidden lines do not overshadow visible lines. 3.4 Lab exercise, converting 3D objects to orthographic drawings. Objective, draft orthographic views, front, top, right side, of a 3D object, e.g., a mounting bracket with holes and slots. Materials, drafting board, T-square, triangles, compass, vellum. Steps, 1. Sketch the front view, capture the most complex face. 2. Project top and side views, use light construction lines for alignment. 3. Refine lines, darken visible edges, add hidden/center lines. 4. Dimension, label critical measurements per ISO/ANSI standards. 5. Review, check alignment, line types, and completeness. Evaluation criteria, accuracy, plus or minus 1 mm tolerance for measurements. Standards compliance, correct use of projection symbols and line conventions. Clarity, neatness and absence of unnecessary details. Chapter Summary. Orthographic projection is the backbone of technical drawing, transforming 3D ideas into universally interpretable 2D blueprints. By mastering multi-view principles, projection systems, and drafting techniques, students lay the groundwork for advanced topics like sectional views and assembly drawings. Up next, Chapter 4 delves into dimensioning tolerances and geometric constraints, ensuring designs meet functional and manufacturing requirements. Design note, include diagrams contrasting first/third angle projections and a step-by-step example of a bracket's orthographic views for visual reinforcement. Chapter 4, Pictorial Drawings and Isometric Projection. 4.1 Axonometric and Oblique Projections. Pictorial drawings provide 3D clarity for non-technical stakeholders while retaining dimensional accuracy. 2 primary methods, axonometric projections, isometric, all axes, x, y, z, are equally foreshortened at 120 degrees angles. Most common due to simplicity and proportional scaling. Dimetric/trimetric, 2 or 3 axes scaled differently, offering varied perspectives but requiring complex calculations. Oblique projections, cavalier, front face true to scale, receding axis at 45 degrees with full depth, distorts proportions. Cabinet, receding axis scaled to half depth for realistic proportions. Use cases, axonometric, technical manuals, assembly instructions. Oblique, architectural interiors or objects with circular front faces. 4.2 Isometric drawing techniques. Isometric sketches balance speed and precision. 1 axis setup, draw vertical line, z-axis, then 30 degrees lines for x and y axis using a 30°/60 degree triangle. 2 Box method, enclose the object in a proportional isometric box, then carve out details. 3 Coordinate method, plot key points using x-y-z measurements, e.g., a bolt's head at 20,10,5. 4 Circles and arcs, use isometric ellipses, for center approximation, or templates. Tools, isometric grid paper, 30°/60 degree triangle, ellipse guides. Avoid overusing hidden lines, prioritize clarity over completeness. 4.3 Dimensioning in isometric views. Dimensioning in 3D requires balancing readability and standards, ISO 129-2 guidelines, aligned dimensions, text and lines parallel to isometric axes. Unidirectional, text horizontal, avoiding rotation. Best practices, place dimensions on visible surfaces, avoiding stacking on a single plane. Use leader lines for holes or radii, ensuring arrows point to feature edges. Reserve isometric dimensioning for illustrative purposes, detailed specs belong in orthographic views. 4.4 Lab exercise, sketching isometric models. Objective, Draw an isometric view of a stepped block with a cylindrical hole, including dimensions. Materials: isometric grid paper, pencils, 2H, HB, ellipse template. Steps: 1. Layout axes, draw X, Y, Z axes at 120 degrees angles. 2. Block outline, sketch a 50 mm x 30 mm x 20 mm rectangular prism. 3. Step feature, carve a 20 mm x 15 mm notch from the top front edge. 4. Cylindrical hole, add a 10 mm hole centered on the step face using an isometric ellipse. 5. Dimension, label overall lengths, step size, and hole diameter using aligned text. Evaluation criteria: proportional accuracy, plus or minus 2 mm tolerance. Ellipse precision, hole alignment with isometric axes. Clarity, legible dimensions and clean line work. Chapter summary: isometric projection bridges the gap between technical rigor and visual intuition, making designs accessible to engineers and clients alike. By mastering axonometric principles, dimensioning strategies, and sketching workflows, learners expand their ability to communicate complex geometries in 3D. Up next, Chapter 5 introduces sectional views revealing internal features hidden in Indiana orthographic and isometric drawings. Design note: include a comparison of axonometric versus oblique projections and a step-by-step isometric sketch breakdown to reinforce visual learning. Chapter 5, Sectional Views and Auxiliary Projections. 5.1 Purpose of sectional views: full, half, offset sections. Sectional views expose internal features of an object by imagining a cut through it with a cutting plane. Types include: full section, cuts entirely through the object, ideal for symmetrical parts, e.g., engine block. Half section, bisects the object to show both interior and exterior, useful for symmetric assemblies, e.g., flanged pipe. Offset section, uses a staggered cutting plane to capture non-aligned features, e.g., ribs, holes, or slots. Key applications: clarify internal complexity without hidden lines. Highlight mating parts in assemblies. Ensure manufacturability by exposing critical interfaces. 5.2 Hatching conventions and material representation. Hatching, cross-hatching, patterns denote materials and enhance readability. Standards: ISO 128-50, specifies patterns, e.g., 45 degrees spaced lines for metal, brick-like patterns for ceramics. ANSI Y14.2, recommends spacing, 13 mm, and line weight, thin, consistent. Best practices: avoid overlapping patterns in adjacent parts. Use different angles for distinct materials. Omit hatching for very small areas to prevent clutter. Common pitfalls: incorrect spacing/angles causing confusion. Misapplying patterns, e.g., using plastic hatching for steel. 5.3 Auxiliary views for inclined surfaces. Auxiliary views project inclined or oblique surfaces to show their true shape and size. Primary auxiliary view projects onto a plane perpendicular to one principal plane, e.g., showing a slanted face's true shape. Secondary auxiliary view projects from a primary auxiliary view for doubly inclined. Chapter 6, CAD Laboratory, Digital Drafting Tools. 6.1 Introduction to CAD software, AutoCAD, SolidWorks, etc. Computer-aided design, CAD, has revolutionized engineering workflows, replacing manual drafting with precision, efficiency, and scalability. Popular tools include AutoCAD, industry standard for 2D drafting and basic 3D modeling, widely used in civil and architectural fields. SolidWorks, parametric 3D modeling software favored in mechanical design for assemblies and simulations. Fusion 360, cloud-based CAD/CAM/CAE tool for integrated design, manufacturing, and analysis. Kasha, advanced surface modeling for aerospace and automotive industries. Key advantages: precision, sub-millimeter accuracy for complex geometries. Reusability, templates, libraries, and legacy designs streamline new projects. Interoperability, export files for CNC machining, STEP, IGES, or 3D printing, STL. Collaboration, cloud platforms enable real-time teamwork and version control. Core principles, CAD retains drafting fundamentals, e.g., orthographic views, dimensioning standards. Mastery of both drafting intent, design logic, and software tools is critical. 6.2 Creating 2D sketches and 3D models. 2D sketching, workflow, 1. Define planes, XY, XZ, YZ. 2. Sketch geometry, lines, circles, arcs, with constraints, horizontal, vertical, tangent. 3. Apply dimensions and relations, parallel, concentric. Constraints, ensure design intent is maintained during edits, e.g., a hole remains centered. 3D modeling, extrusion/revolve, convert 2D sketches into 3D forms, e.g., shafts, brackets. Boolean operations, combine/add/subtract volumes, union, difference, intersection. Parametric modeling, edit dimensions to automatically update geometry, e.g., resizing a gear tooth. Surface modeling, craft complex curves, e.g., car bodies, aerodynamic shapes. Best practices, start with simple sketches, avoid over-constraining. Use symmetry and patterns to reduce redundant work. 6.3 Layers, blocks, and parametric design layers, organize elements, e.g., dimensions, center lines, hidden features, into separate layers for clarity. ISO 13567 standardizes layer naming, e.g., dim for dimensions, hid for hidden lines. Blocks, reusable symbols, e.g., fasteners, electrical components, stored in libraries. Attributes, add metadata, e.g., part numbers, materials, to blocks. Parametric design, design variables, link dimensions to equations, e.g., gear pitch equals module times teeth count. Top-down design, assemble components contextually, e.g., a piston size to fit a cylinder. Design tables, drive multiple configurations, e.g., different bolt lengths, from a spreadsheet. 6.4 Lab exercise, from manual to digital drafting objective, convert a manual orthographic drawing, e.g., Chapter 3's mounting bracket, into a parametric CAD model. Software, AutoCAD or SolidWorks, instructor's choice. Steps, 1. Import/reference, scan the manual drawing or use it as an underlay. 2. 2D sketch, recreate front, top, and side views with constraints. 3. 3D model, extrude sketches, add holes/fillets, and apply materials. 4. Parametric links, define variables, e.g., hole diameter equals 0.5 times bracket thickness. 5. Documentation, generate orthographic and isometric views with automated dimensioning. Evaluation criteria, accuracy, match manual drawing within plus or minus 0.5 mm, parametric flexibility, adjusting variables updates the model without errors. Organization, proper use of layers, blocks, and annotations. Chapter Summary. CAD transforms theoretical drafting skills into practical, scalable solutions. By integrating layers, parametric logic, and 3D modeling, engineers unlock rapid prototyping, simulation, and global collaboration. However, CAD's power lies in its foundation principles honed through manual drafting. Up next, Chapter 7 explores advanced dimensioning, tolerancing, and GD&T, ensuring CAD models meet real-world manufacturing requirements. Design note, include screenshots of CAD interfaces, AutoCAD/SolidWorks, with labeled toolbars. Provide a side-by-side comparison of manual versus CAD-generated drawings. Highlight common pitfalls, e.g., over-constraining sketches, ignoring layer standards. Chapter 7, dimensioning, tolerancing, and surface finish. 7.1 GD&T, geometric dimensioning and tolerancing. Basics overview. GD&T is a symbolic language for defining part geometry and allowable variations, ensuring functional fit and interchangeability. Governed by ASME Y14.5, it replaces traditional plus or minus tolerancing with precise control over form, orientation, and location. Key concepts: datums, reference points/planes, e.g., datum A, B, C, establishing the measurement coordinate system. Feature control frame, https://via placeholder.com/400x100, text equals symbol tolerance datum, symbol, geometric characteristic, e.g., flatness, perpendicularity. Tolerance value, allowable deviation. Datum references, measurement basis, e.g., datum A. Common GD&T symbols. Symbol name description -- flatness surface must lie between two parallel planes. Concentricity median points align with a datum axis. Perpendicularity surface/axis at 90 degrees to a datum. Cylindricity maintains a perfect cylindrical form. YGD&T reduces ambiguity in manufacturing. Allows functional tolerances, reducing cost compared to overly tight plus or minus tolerances. 7.2 Surface texture symbols and annotation. Surface finish parameters, RA, average roughness arithmetic mean of surface deviations. RZ, maximum height average difference between highest peaks and deepest valleys. Lay, direction of surface pattern, e.g., parallel, circular. ISO 1302 symbols. Basic symbol, check mark, with added annotations, RA 1.6, surface roughness of 1.6 m, machining allowance, additional material for finishing, e.g., 0.5. Application example, a bearing seat may require RA 0.8 for smooth operation, while a non-functional face uses RA 3.2. 7.3 Tolerance stack-up analysis methods. 1 Worst case analysis, sum of max/min tolerances, conservative, expensive. Example, 3 parts with plus or minus 0.1 mm total stack, plus or minus 0.3 mm 2. Statistical analysis, RSS, tolerance superscript 2, cost effective, assumes normal distribution. Example, 0.1 superscript 2 plus 0.1 superscript 2 plus 0.1 superscript 2, equals plus or minus 0.173 mm. When to use, worst case, safety critical assemblies, e.g., aerospace. Statistical, high volume production, e.g., automotive. 7.4 Lab exercise, applying tolerances to engineering drawings. Objective, apply GD&T and surface finish symbols to a shaft drawing for a gearbox. Steps, 1. Identify critical features, bearing seats, tight cylindricity and RA 0.8. Keyway, parallelism to datum A. 2. Select datums, datum A, central axis. Datum B, mounting flange face. 3. Apply GD&T, perpendicularity 0.05 mm relative to datum A, circularity 0.02 mm on bearing seats. 4. Add surface finish, bearing seats, RA 0.8. Non-functional surfaces, RA 3.2. Evaluation criteria, correct use of symbols and datums. Balance between functionality and manufacturability. Chapter Summary. GD&T and surface finish specifications bridge design intent and manufacturing reality. By mastering tolerance stack-up analysis and symbolic annotation, engineers ensure parts meet functional requirements without unnecessary cost. Design note, include annotated diagrams of a gearbox shaft with GD&T and surface symbols. Provide a tolerance stack-up calculation example comparing worst case versus RSS. Highlight common errors, e.g., overspecifying RA, misaligned datums. Up next, Chapter 8 explores assembly drawings and bill of materials, BOMs, integrating toleranced components into cohesive systems. Chapter 8, Assembly and Detail Drawings. 8.1 Components of assembly drawings, exploded views, BOMs. Assembly drawings visually communicate how components fit together, ensuring correct alignment and functionality. Key elements include: exploded views, illustrate part relationships and assembly sequence by separating components along axes. Use leader lines to maintain clarity. Bill of materials, BOM, lists part numbers, descriptions, quantities, materials, and standards, e.g., ISO 7573, ASME Y14.34, example BOM entry, part no. Description: quantity, material standard GB001 hex head bolt M10X404 stainless steel ISO 4017, balloon callouts, numbered labels linking parts in the drawing to the BOM. Purpose: facilitate assembly, maintenance, and quality control. 8.2 Detail drawings for manufacturing. Detail drawings provide all information needed to manufacture individual parts, essential elements, dimensions with tolerances, GD&T from Chapter 7. Surface finish, RA, RZ, and heat treatment requirements. Material specifications, e.g., ASTM A36 steel. Critical features, threads, grooves, welds. Manufacturing notes, machining processes, e.g., finish all surfaces to RA 3.2. Post-processing, e.g., anodize per mil A8625. Best practices, separate views for complex features, e.g., sectional views for hidden holes. Reference standards, e.g., ASME Y14.100, for consistency. 8.3 Fasteners, welds, and standard parts. Fasteners, symbols, use simplified representations for bolts, nuts, and washers, e.g., ISO 6410. Annotations, specify thread type, M10X 1.5, length, and grade, e.g., grade 8.8. Welds, ISO 2553. Symbols, fillet weld, groove weld, and weld size, e.g., 5 mm leg length. Example, 5, fillet weld, 5 mm, arrow side. Standard parts, use catalog references, e.g., Dowdy Seal MS29513-010, to avoid overdetail. 8.4 Lab exercise, creating an assembly drawing from parts. Objective, draft an assembly drawing for a simple gearbox, including exploded view, BOM, and critical detail callouts. Steps: 1. Select views, front view, assembled state, plus exploded isometric view. 2. Add balloons, label all parts numerically, linking to the BOM. 3. Detail interfaces, specify gear meshing tolerances, e.g., backlash plus or minus 0.05 mm. Annotate bearing press fit, H7/S6. 4. BOM, list gears, shafts, fasteners, seals, and materials. 5. Manufacturing notes, include torque specs for bolts, e.g., Tighten to 25 Nm. Evaluation criteria, clarity, logical view arrangement and legible annotations. Completeness, all parts referenced in BOM with correct quantities. Standards compliance, proper weld/fastener symbols and GD&T. Chapter summary. Assembly and detail drawings transform individual components into functional systems. By mastering exploded views, BOMs, and manufacturing annotations, engineers ensure seamless production and assembly. Design notes, include a gearbox exploded view with balloon callouts. Provide a weld symbol cheat sheet, ISO 2553. Highlight common errors, e.g., missing part numbers, overcrowded views. Up next, Chapter 9 introduces advanced CAD workflows for simulation and prototyping, bridging design to real-world testing. Example, exploded gearbox, https://viaplaceholder.com/600x400, text equals exploded plus gearbox plus with plus balloons plus and plus bomb, caption, exploded view of a gearbox with balloon callouts and bomb. Chapter 9, Engineering Drawing Applications 9.1 Mechanical Systems, Gears, Bearings, and Linkages Gears, Representation, Simplified Tooth Profiles, ISO 2203, with key parameters, module, pressure angle. Annotations, pitch diameter, root diameter, and gear ratio, e.g., 20:1. Assembly, show meshing gears with proper center distances and backlash tolerances. Bearings, symbols, simplified cross sections, ball, roller, with callouts for type, e.g., 6204 deep groove ball bearing. Mounting details, shaft/housing tolerances, H7/K6 interference fit. Linkages, kinematic diagrams, schematic representations, ISO 3952, of 4-bar linkages, sliders, or cams. Critical dimensions, crank lengths, pivot points, and angular limits, e.g., 0 degree 90 degree rotation. Standards, ASME Y14.7 for gear drawings. ISO 8826-1 for bearing symbols. 9.2 Civil Engineering, Architectural and Structural Drawings. Architectural drawings, plans/elevations, scale 1:100 floor plans with room labels, door/window schedules. Sections, reinforced concrete footings, HVAC layouts. Annotations, material callouts, e.g., CMU blocks, gypsum board. Structural drawings, beams/columns, symbols for steel I-beams, e.g., W12x26, or rebar layouts, ACI 315. Foundations, grid lines, load-bearing walls, and soil specifications. Codes, AISC, steel, ACI, concrete, Eurocodes, EU. Best practices, use hatching for materials, e.g., diagonal lines for concrete, dots for insulation. Coordinate with MEP, mechanical, electrical, plumbing, drawings. 9.3 Electrical and Electronics, circuit layouts and schematics. Schematic diagrams, symbols, resistors, zigzag, capacitors, parallel lines, ICS, rectangles with pin numbers. Standards, IEEE 315/ANSI Y32.2 for component symbols. PCB layouts, layer stack up, define copper layers, vias, and traces, IPC 2221. Footprints, match component sizes, e.g., 0805 resistor, SOIC 16IC. Wiring diagrams, cable routing, labels for wire gauges, e.g., 12 AWG, and terminal blocks. Safety, grounding symbols, and NEC/ISO 7010 compliance. 9.4 Lab exercise, discipline-specific drawing projects. Objective, create a drawing tailored to your field, mechanical, civil, or electrical. Options, 1 mechanical, gear pump assembly with GD&T and bomb. 2 civil, single-story house plan with foundation details. 3 electrical, Arduino-based sensor circuit, schematic and PCB layout. Steps, 1 research, identify relevant standards, e.g., ASME, AISC, IPC. 2 draft, use CAD tools, AutoCAD, Revit, Eagle, or manual drafting. 3 annotate, include critical dimensions, symbols, and notes. 4 review, cross-check against industry checklists, e.g., ANSI Y14.100. Evaluation criteria, accuracy, compliance with functional requirements. Standards, proper use of symbols and codes. Presentation, clarity and completeness. Chapter summary. Engineering drawings adapt to diverse fields, yet their core principles, precision, standardization, and clarity remain universal. Whether designing a gear, a skyscraper, or a circuit, these drawings translate ideas into actionable blueprints, underscoring the interdisciplinary power of technical communication. Design notes include a gear schematic, architectural floor plan, and PCB layout as visual aids. Highlight interdisciplinary projects, e.g., robotics integrating mechanical, electrical, and structural elements. Warn against siloed design, e.g., civil engineers ignoring MEP coordination. Up next, Chapter 10 explores emerging trends like BIM, building information modeling, and AI-driven design tools, preparing readers for the future of engineering visualization. Chapter 10, Advanced Topics and Emerging Trends. 10.1 3D Printing and Rapid Prototyping. From CAD Model Overview. 3D printing revolutionizes manufacturing by converting CAD models directly into physical objects through additive processes. This section explores file formats, STL, standard tessellation language, AMF, additive manufacturing file, and 3MF for high-fidelity data. Design considerations, support structures, essential for overhangs, optimize placement to minimize post-processing. Tolerances, account for layer adhesion and shrinkage, e.g., plus or minus 0.1 0.5 mm depending on technology. Material constraints, thermoplastics, FDM, resins, SLA, and metals, SLS/DMLS. Technologies, FDM, fused deposition modeling cost-effective for prototypes. SLA, stereolithography high-resolution finishes. SLS, selective laser sintering durable, complex geometries. Impact on engineering drawings, shift from traditional machining notes to layer orientation and infill density specifications. Emphasize design for additive manufacturing, DFAM, principles to leverage topology optimization. Case study, redesigning a bracket with generative AI tools to reduce weight by 40% while maintaining strength. 10.2 BIM, building information modeling, integration overview. BIM transcends 3D modeling by embedding data, cost, materials, timelines, into collaborative, multidisciplinary workflows. Key features, clash detection, resolve conflicts between mechanical, electrical, and structural systems pre-construction. Life cycle management, from design, ISO 19650, to facility maintenance. Interoperability, IFC, industry foundation classes, ensures compatibility across software, Revit, AutoCAD MEP. Engineering drawing synergy, automated extraction of 2D views and schedules from BIM models. Real-time updates ensure drawings reflect revisions across disciplines. Example, a hospital project where BIM integration reduced rework by 20% through coordinated MEP layouts. 10.3 AI-driven design and automation in drafting applications. Generative design, algorithms produce optimized geometries based on load, weight, and material constraints, e.g., Autodesk Fusion 360. Automated drafting, dimensioning, AI tools suggest placements per ASME Y14.5. Error checking, flag mismatched tolerances or missing annotations. Component libraries, ML-driven recommendations for standard parts, e.g., bolts, bearings. Ethical considerations, bias mitigation, ensure training data diversity to avoid skewed solutions. Human oversight, maintain engineer accountability for AI-generated designs. Case study, an automotive firm reduced chassis design time by 60% using generative AI while adhering to safety standards. Number 10.4 Lab exercise, prototyping a 3D printed component. Objective, transform a CAD model into a functional 3D printed part, validating design intent against real-world output. Steps, 1. Model preparation, export gear housing CAD model to STL. Use slicing software, Cura, Prusa Slicer, to set parameters, layer height, 0.2 mm, infill, 20% hexagonal, supports, tree style, minimize material use. 2. Print execution, monitor first layer adhesion and temperature settings. 3. Post-processing, remove supports, sans surfaces, and measure critical dimensions, e.g., bore diameter. 4. Validation, compare printed part to original drawing using calipers, plus or minus 0.2 mm tolerance. Test fit with mating components, e.g., shaft insertion. Evaluation criteria, dimensional accuracy and surface finish. Functionality in assembly context. Chapter summary. Advanced tools like 3D printing, BIM, and AI are reshaping engineering workflows, yet foundational drawing principles remain vital. By embracing these technologies, engineers enhance precision, collaboration, and innovation while navigating ethical and practical challenges. Design notes include screenshots of generative design outputs and BIM clash detection. Provide a comparative table of 3D printing technologies, speed, cost, resolution. Highlight interdisciplinary projects, e.g., AI-optimized bridge components validated via BIM. Future outlook. As AI and additive manufacturing evolve, engineers must balance automation with critical thinking to drive sustainable, human-centric design. Appendices and glossary for engineering drawing textbook. Appendix A, Drafting Standards and Symbols, ISO/ANSI. Quick reference, content, line types, tables comparing ISO 128 and ASME Y14.2 conventions, e.g., continuous, dashed, chain lines. Dimensioning symbols, side-by-side ISO 129 and ASME Y14.5 symbols for diameter, radius, R, and tolerances, plus or minus. GD and T symbols, chart of geometric tolerancing symbols, flatness, concentricity, per ASME Y14.5/ISO 1101. Welding symbols, ISO 2553 versus AWSA 2.4 standards. Surface finish, comparison of RA, ISO 4287, and RMS, ASME B46.1. Format, tables with brief descriptions and visual examples. Appendix B, Common errors and troubleshooting. Common errors, line weight issues, using thick hidden lines instead of thin dashed lines. Misaligned views, front/top views not sharing width dimensions. Dimension clutter, overlapping or redundant dimensions. Troubleshooting, CAD specific, resolving over-constrained sketches, layer mismatches. Visual aids, side-by-side incorrect versus corrected diagrams. Examples, error, hidden lines overriding visible edges. Fix, adjust line hierarchy, visible hidden center. Appendix C, blank drawing sheets and templates. Templates, manual drafting, A4/A3 sheets with ISO compliant title blocks, fields for name, scale, revision. CAD templates, downloadable .dwg/.dxf files with preset layers, dim, hid, center. Formats, orthographic, 3-view, isometric, assembly, and sectional templates. Appendix D, practice problems and lab worksheets. Practice problems, beginner, redraw a 3D object in orthographic views. Advanced, apply GD and T to a machined bracket. Lab worksheets, CAD exercise, model a gear pump with parametric constraints. Manual drafting, create a sectional view of a flange coupling. Solutions, separate instructor's manual with step-by-step explanations. Glossary, key terms and definitions, entries, orthographic projection, a 2D representation of a 3D object using multiple views, front, top, side, dot. Datum, reference plane/axis used to establish measurement origins, ASME Y14.5, dot. BOM, bill of materials, list of parts, quantities, and specifications in an assembly, ASMEY 14.34. Format, alphabetical order, bold terms, cross-referenced to chapters. Design notes, user-friendly navigation, clear headings, color-coded tables in Appendix A, cross-referencing, Chapter 7 references Appendix A for GD and T symbols, labs link to Appendix D, consistency check, ensure symbols/terms align with main text, e.g., for perpendicularity. Final touches, accuracy review, validate standards, e.g., ISO 129-2 for dimensioning. Visual aids, include QR codes in Appendix C for digital template access. Accessibility, glossary terms indexed for quick lookup. This structure ensures appendices and glossary enhance the textbook's utility, providing students with practical tools and quick references to master engineering drawing fundamentals.